Okay, as part of our journey away from VMware in conjunction with products like the CX10000, we have to rely on other forms of isolation techniques where pVLAN doesn't exist. If we want to perform east-west microsegmentation between virtual machines or containers that reside inside the same host, then we certainly have a challenge if pVLAN doesn't exist in the current Linux implementations. So the challenge we have right now is customers are looking to move away from using Enterprise Plus licensing inside VMware, whether that's with VVF or VCF, and ultimately migrating away from technologies such as VMware NSX. In our solution, we leverage pVLAN to isolate workloads, but importantly, we leverage IP local proxy ARP to provide a bridging solution between virtual machines that are looking for connectivity to devices on the same subnet. So effectively, the CX10000 represents the MAC address of the destination workload, and we also route between subnets, performing both micro and macro segmentation. So how do we do this with a Linux-based platform? So if we look at how Linux effectively is built under the hood, we have the Linux kernel, we have different networking technologies. So historically, we have physical interfaces attached to the device. We have logical interfaces which use the underlying physical interface or the lower interface that allow us to perform or leverage things like VLAN tags. And we then attach these interfaces to different networking technologies, such as a Linux bridge, which is the historical bridging and switching implementation inside Linux. There is a dedicated kernel module for Linux bridging, which needs to be installed, as well as specific user land tools to interrogate the bridge or the switch. Modern implementations leverage OVS, so there is an Open vSwitch module that allows us to interrogate using OVS tools, and we then have some underlying rules for OpenFlow directly built into the kernel, whether that's provisioned on a machine-by-machine basis or using a centralized OpenFlow controller. There is also this other approach as well, both Mac VLAN and Mac VTAP, that allow us to create a logical interface that's directly attached to the lower interface. So for example, I can have a Mac VTAP interface attached to a physical interface that's using a VLAN, so VLAN 10 is what I'm using in my examples. And this effectively bypasses the need to have the bridge module installed or Open vSwitch. And it does bypass a fair majority of the Linux kernel as well. So it actually has lower latency, and because we're assigning essentially a virtual interface to a container or virtual machine, it has its own MAC address. It does, however, in a default scenario, bridge between devices that are attached to the same lower interface. So we need to make sure that we don't perform that as well, and we end up sending traffic towards the CX10000 where local proxy ARP is still configured. In any of these approaches, there is only a single VLAN tag, whether we're using Mac VTAP, bridge isolation, or OpenFlow, as well as some other approaches, and they all have a single VLAN tag. So as far as the upstream router is concerned or switch is concerned, it just sees these as single tag devices, effectively mimicking a bare metal type approach as well. So those approaches would be things like obviously Mac VTAP and Mac VLAN, which are both very similar. Linux bridge interface isolation, which I'll dig into. OVS OpenFlow rules to ensure that one MAC address cannot communicate to another. There's other approaches such as EV tables, which is essentially a layer 2 access list for a Linux bridge. And then we can even use things like SR-IOV interfaces, so directly mapping a logical PCI channel into a VM. But there will be struggles around performing migrations of these sorts of workloads. Tested platforms, I'm going to really focus on the bare metal Linux KVM and container experience before we start looking at orchestration platforms. Understanding how the Linux kernel works and how it performs isolation of workloads is important, because effectively every orchestration platform above this that leverages Linux will be using the underlying Linux networking techniques to forward to switch traffic between VMs and into the physical network. So there's a lot of reliance on existing OBS bridging or switching, Linux bridges, Mac VLAN interfaces. None of these vendors have really gone off and created their own networking component as part of the Linux kernel because that has already been done for them. My default server install, I've got a bunch of different utilities, kernel modules, etc. installed into my servers, so server 1 and server 2, which are both just Ubuntu 24.04 servers. And that's it. So making sure I have KVM installed, QEMU, Linux bridging, OBS, as well as installing Incus directly from the upstream 6.6 release or current stable release as well. And I'm using NFS in my background as well in my lab here just to ensure I've got the ability to move virtual machines around if need be as well. So focusing on KVM, KVM is the kernel virtual machine. It provides effectively a type 1 hypervisor environment directly inside the Linux kernel. Is there to provide optimization of virtualization inside the kernel. It's not responsible for any underlying networking at all. So when a customer says to me, we need to provide isolation for KVM, KVM isn't responsible for networking. It's the responsibility of the underlying Linux networking stack to achieve that. And KVM essentially just leverages that for attachment. And two approaches I'll look at will be Mac VTAP, Linux bridge isolation, as well as Open vSwitch. So probably should change that slide as well. We'll dig into OBS as well. And also, I think it's the three approaches, yeah, maybe EV tables. So digging into this as well, we've gone through this slide as well. So KVM is a Linux kernel module. It's responsible for converting the kernel into effectively a type 1 hypervisor and directly leverages CPU feature sets such as AMD V and Intel VT, which need to be present inside the host for virtualization. And then things like QEMU, which is effectively the machine emulation layer that leverages KVM if it is present for acceleration or hardware-based acceleration in the CPU for virtualization. If KVM doesn't exist, it'll run in user land, which is a lot slower. So there's actually a combination of two things, QEMU and KVM, that share a common API called libvirt. There is other APIs as well, but libvirt seems to be the most common and prevalent API that's leveraged to directly talk to both of these two components. Centralized tools can be things like Virtual Machine Manager, which simply makes API calls into libvirt, which is an RPC-based system. There is other orchestration platforms as well that will be using the same API, but it's also possible they have developed their own APIs to talk into these platforms as well. So QEMU, KVM, libvirt are not responsible for configuring the underlying physical interfaces or lower interfaces for attachment. It can create logical interfaces which attach to those, but there may need to be additional work done by the user or the orchestration platform to provision the lower layer interfaces and maintain consistency between hosts as well. And some orchestration vendors will do that as well and have created their own APIs and user land tools to make that happen. So if we look at some of the landscape, Red Hat, CoreOS have things like Cockpit, which allows you to configure the VMs. Obviously, there's other tools from Red Hat as well as part of OpenShift, OpenShift V, which are leveraging KVM and QEMU under the hood as well. Ubuntu has things like LXD and MAS for provisioning across multiple bare metal servers. SUSE has their own toolset in Yast. OpenStack Nova, which is obviously very prevalent out there as well, is simply just leveraging KVM and QEMU under the hood. Proxmox has built their own custom API layer as well, so they've got a REST-based API that's talking directly into KVM and QEMU, and also allows for the creation and provisioning of the underlying lower layer interfaces as well, and even provisioning those across multiple hosts simultaneously. And other tools, Overt, Incus, These all leverage the underlying KVM QEMU combination, so it's really important to understand how they work as well. So if you're effectively using a Linux-based virtualization platform, there's a very good chance you'll be leveraging KVM and QEMU for virtualization of VMs. And if we're looking at containerization, it's probably going to be things like LXC as well. So the only exception really would be if you're using XCP-NG, which is based on Xen, which is using a different approach to provide the same outcome. But I'm going to focus on KVM and LXC. In my lab, I've got 2 servers. We'll use server 1 initially. I've gone through and pre-configured all the images that I need to download and replicate and stage for my virtual machines. I need to provision my lower layer interfaces as well. So if I look at server 1, I don't have an interface called VLAN 10, so I do have some physical interfaces, so ENS 18, 19, and 20, which are attached to my CX switch. They're all attached to the same, to a trunk interface on that CX switch. So if I want to configure a logical interface called, I'm going to call the interface VLAN 10. It's going to be attached to ENS 19 as a physical interface, so I'm creating a logical interface VLAN 10, giving it a VLAN ID of 10. Now this name here can be whatever I want as well. So this makes it pretty easy to have a consistent name for my logical interface across multiple guests, even if the physical interface is different. And it's going to become sudo here as well, because for the sake of demonstration. Now that interface will be marked as down as well. So here we need to make sure we bring the interface up as well. Okay, so VLAN 10 is now up. We should better see if there's any traffic on there. Probably nothing. All right. This is my IPv6 communication going out as well. Not seeing anything on there yet for cool. Okay, so now I've created my logical interface, VLAN 10 attached to ENS 19, which is attached to my upstream switch. The CX10000 switch just has a trunk interface. I've still configured the native VLAN. I could remove that. And the only thing I need to configure really is local proxy ARP. No need to have pVLAN configurations, private VLAN, whatever. It's just a single tagged VLAN interface. I've configured an IP address on this subnet, so 192.168.10.1 will be my gateway. There is no MAC address configured. It's just using the default MAC address of that interface. Okay, so we should notice that this MAC address will be the one that it uses for any local proxy ARP configurations. Right, so I'm going to bring up my 2 VMs. I have already configured the XML file. So it is using it's called VM1, using a disk called VM1.image. It's pre-configured with an IP address of 192.168.10.41 and 42 for the other one. And you'll see it's now associated to VLAN 10, the logical interface. Importantly, it's set to mode of private. If I do not have this here, then it will be set to mode type bridge, which means that these 2 VMs will communicate directly to each other, not through a bridge, but through the tap interface. And I've told it to use a MAC VTAP interface for attachment, and we'll see that shortly. This is actually the default behavior. If you don't define this, it will use that interface anyway, and that's all I have to do. So. And VM2 is the same as well, just using a different disk, a different name. So let's start. There shouldn't be anything running. Okay. VM1 started, VM2 started. Okay, so those 2 VMs are running, and these are using, you should see, IP dev. What's the command? Losing my mind. IP link, sorry. Right, these two interfaces have now been created for me. So there's two MAC addresses have been allocated and assigned to this interface. So this will be for VM1 and VM2. Okay, let's log into the VMs and look. Okay, so this MAC address here corresponds to this one. Okay, that's good. Interfaces are up. Okay, it's already seen the default gateway. Now obviously I can ping myself. 41 and 42 is the VM2. Now the first ping here is quite slow because obviously it's waiting for an ARP response from the neighbor. And we see that the MAC address of the switch, of the remote device is actually the CX10000. So we have microsegmentation now. I have two VMs, KVM-based VMs sitting inside the same host, sharing the same logical VLAN-based interface that are having to traverse through the CX10K using IP local proxy ARP. Now I have had to disable ICMP redirect on the switch as well because the CX10K will try and send redirects on behalf of the target VM as well. So we don't want that behavior. So that's slightly different from pVLAN, which must disable ICMP redirects on the promiscuous VLAN, I guess, or the isolated VLAN. So we don't see that behavior. So that's MAC VTAP. MAC VLAN also exists as well, but MAC VTAP is essentially leveraging MAC VLAN and creates these logical interfaces for us as well, which we've seen. So actually I can leave this ping running here. And we can do things like get this interface here. In fact, we just have to do that. All right, so we can actually capture the traffic on these interfaces. MAC VLAN doesn't create these logical interfaces either. It's hidden inside the kernel. All right, let's just go and turn off that that ping. Right. Let's move on to a Linux bridge, which is also the other historical approach that a virtual machine would be attached to a bridge. So a bridge, I can have a look and see what we've got in the way of bridges already. There's always a default bridge called VIR-BR0. It doesn't have any interfaces attached to it. I'm going to create a new bridge. A new bridge will be called, okay, I'm going to create a new interface, a new logical interface called BR-VLAN10. So this is the same as what I had for my interface before called VLAN10, but I can't reuse an interface associated with a Mac VLAN. I don't think I can. We can try that. So let's create a new one here. Okay. Okay, there it is there. And now I'm going to attach this to a new bridge. Okay, so I've made a new bridge called BR-VLAN10. I've attached the interface, the logical interface BR-VLAN.10, which is using ENS19 as a physical, to that interface. And we'll see we have this interface created. I don't know what will happen if I try and attach Right, so it's already a member of some other bridge. This VLAN 10 is using Mac VLAN, so internally inside the kernel, it's not actually letting me do that at the same time, which is fair enough. That would be confusing. Okay, I need to make sure that everything is set to up. Okay, make sure my physical interface is up, which it probably already was. Yep. Make sure that my logical interface is up, which it is. Okay, sometimes they're not. And then set the bridge to up as well. Okay, cool. Here is our bridge. We're now going to attach two virtual machines to this. So I have VM3 and VM4. So 3 and 4, which already have pre-assigned IP addresses of 10.43 and 10.44. They are using a type of bridge, interface type, and attached to this bridge. And the other VM is the same config. The only difference is the name of the disk image they're using and the name of the host. So let's start these two up. Ooh, not that. Right, and it now has created these two logical interfaces, VNet 0 and VNet 1. So VNet 0 and VNet 1 have been created and attached to that bridge. As you can see, they're attached to that bridge. The bridge can be called whatever you want. I'll just call it BR-VLAN 10. And we can see that it actually has, no, because it's trunking on VLAN 10. Okay. Rightio. Let's have a look at those VMs. This is where things are going to get a little bit different from Mac VLAN. List, okay. Don't do that. Okay, so the interface here is up. Here's its MAC address. Okay. It should have an address as well. Okay. Okay, it's seen the default gateway already. Let's see if we can ping the original two VMs, 41 and 42. They should have the MAC address of the CX10000. They do. Cool. Okay, now what happens if I ping 10.44? That works, good. Notice how the latency for the ARP response was really low, 1.2 here as opposed to what we normally see. So let's have a look at the ARP table. Oh, right. So with Linux Bridge, my two VMs, it's now communicating directly through the Linux Bridge. I need to change this diagram to actually have the bridge here as well. Let's add a little bridge here as well, because that's what a bridge is, effectively just a switch. Okay. So traffic is now coming through here, through this switch effectively, and traversing here. So there's no micro segmentation taking place right now in this design. Now, why is that? By default, interfaces attached to a bridge, like VNet 0 and VNet 1, are not isolated. They are always able to communicate directly and broadcast directly through the switch. So I've written this tool which shows me the status of isolation for each interface. So right now these interfaces are not isolated. There's other ways to look at it, but it's actually not something that's very very simple. I think we can look at the can we look at the, there is a way to actually look at the status of it as well. Okay, I think we can, I need to find it. All right, I'll get to it. Actually, I could probably look at my code, couldn't I? What is it doing? Okay, it's looking inside here. Right, but it's not something that's actually very straightforward to see if the interface is isolated. But by default, these interfaces are always set to not be isolated and obviously to switch efficiently through the software switch or the bridge. Right, so the way we change that is we do look at our bridges, get our two names of interfaces, VNet 0 and VNet 1. Now these interfaces will change. If I stop this VM and bring it back up again, I can't guarantee it'll be set to VNet 0. If I move the VM from one host to another, again, we can't guarantee what that will be. Now it typically is called VNet something or TAP something or VETH something as well. There isn't super consistency between different implementations of this as well. But one thing is for sure that interface isn't consistently named, and the isolation status will not be set if it moves somewhere else as well. So if it is set to isolated on this server and we migrate it somewhere else, then the interface name will change. The isolation status will flip back to being open as well. So what we do is we basically issue this command here. So I need to set VNet 0. Let's just run my command again. See, this is now set to isolated, and we'll also do the same for 1. This tool is on my GitHub repo as well. Right, so now they're both set to isolated. So if we log back into that was a really inefficient way of doing that. Okay. So right now the MAC address of this machine here is directly mapped through. So if I ping that now, it probably won't work because we've blocked it. So it's set to isolated. So I need to clear the ARP table. And we don't have any entries. And now if I ping that, and we wait patiently. Okay, it's still working. I need to be more patient. But you can see that there's additional steps that need to be configured. I need to configure the interfaces as being isolated. I need to ensure that the ARP table isn't already populated with an existing entry and clear it. There was a delay as well. It looks like I needed to actually have an ARP entry for the gateway as well. So interesting. There's a couple more moving parts if I used a Linux bridge. We're going through additional layers inside the Linux kernel as well, so this will have slightly higher latency. We probably can't really see that here. Let's have a look. So need to get some better tools and to sort of measure the average latency. They are both using the same physical underlying NIC, just a different port. Uh, 41. Okay, that's actually quite a bit different. So the top one is using Linux Bridge interfaces with isolation, and the bottom one is using a Mac VLAN interface. Oh, I'm pinging myself. Okay. Oh, with this approach, it's very difficult to actually see any difference. Yeah, maybe 0.1. A little bit different. It'd be interesting to get some proper tooling in here and actually try this out. Something I might do in my next video. Okay, we now have VM1, 2, 3, and 4 running. The first two are using Mac VLAN, or Mac VTAP, sorry. The second two are using a Linux bridge. Let's configure OVS. So KVM isolation using OVS. So OVS does not have an isolation option like Linux Bridge does. So that leads us to have some further issues here as well. So we'll be going through a separate OVS switch. Now typically with OVS there's only a single switch or a single bridge, whereas with Linux bridges you could have multiple. So it's much more like sort of a modern switching implementation sitting in software. It has its own API. It's very advanced in what it can do. It supports different types of encapsulations and overlays as opposed to just VLANs. So it's very extensible and quite widely used. But as you'll see, it's probably a lot more problematic as well. So I need to set up, let's just see what I've got. OBS, CTL is the main command. You look at the bridges, the OBS switch, we do not have one. Okay, so I'm going to make one. I'm going to call it BR-OBS. Right, so now I have created a bridge called BR-OBS. Oop, what happened there? Okay. I'm going to add a physical port to it. So I've got another one called ENS20, which is my physical interface. Okay. So now I've attached physical port interface ENS20 to this bridge. Right. And by default, this will be a trunk port as well. You can restrict what VLANs will be sent on there, but the default behavior is to have it set up as a trunk. I'm going to make sure it's up. It probably already was here, right? So you can just make them up, down if you want to. And we're going to, okay, we don't have to do anything else, right? I could restrict what VLANs are seen on that trunk if I want to, but by default the interface is configured as a trunk. Now I've got two VMs, VM5 and VM6. So this is a bit different again. I attach the VM to a bridge of OBS. It's the same config here as a Linux bridge, but the source bridge now, it knows that it's an OBS. I'm going to associate this VM with VLAN tag ID of 10, and VM6 is the same config. So we're going to start this. Let's have a look at our. Okay, so we've actually got a new interface called VNet2. So before we had 0 and 1, now we've got 2, and presumably we'll get 6. Yeah. Oh, okay. We should have these two. 2 and 3. 2 and 3. Interesting. Where did we net 0 go? Okay, we'll look into that. Okay, cool. I'll revisit that one. Okay, we've started these two VMs and now we're going to log into them. Okay. VM5. Okay, we've got an address. Okay, we've already seen the default gateway. So 10.46 is my, that was really fast as well, that ARP response. And no surprise, the MAC address is directly reachable through the attached OVS bridge. Okay. So we cannot do bridge interface isolation like we can with the Linux bridge. So we have to take a different approach. So if we look at a different command now, open flow controller command, dump flows from our switch. Okay, so right now the default behavior is just to send all traffic, which means that it'll be using every interface to flood and forward in the most efficient manner through the switch. So we need to change that behavior. So I've written a script to speed this up for us, which is simply going to take the MAC address of every single VM on that bridge and ensure that they cannot communicate to each other directly. But only do this for the VMs, not for the default gateway. So we can look at our flow table now, and that's different. All right, so our flow table says that traffic coming into VNet2, we need to modify the traffic and tag it with VLAN 10 and send it out to ENS20. And the same goes for my other VM. And then when traffic comes back in on ES20, for destined for that MAC address, we strip the VLAN off and we send it directly to the VM. So we've had to leverage the open flow rules or table to directly manipulate traffic direction. So once it does this, that's fine. Traffic cannot communicate to each other directly, and then everything else is just hitting the default rule at the bottom, which is to act as normal. So if I spun up another VM, we'd have to run this again. If I move the VM from one server to another, I'd have to make sure that I rerun this as well. So there's lots of moving parts when this is actually functional. You could have a centralized OpenFlow controller that could do this for you as well, but I'm doing this on a machine-by-machine basis at this point. So now I've restricted this. Okay, so we look at we probably can't ping that because now I've got traffic being blocked. So let's clear the and again, we see this sort of behavior where it's not immediately responding. Let's give it a second. There we go, that took a while. So IP local proxy ARP kicked in on the CX10K. There was a delay while that occurred. And why did I do that for? Okay, that's quicker. Okay, so now we have isolation occurring here. So I should be able to ping any host. Obviously my default gateway, 41, 42, that's myself, 46. Right, so micro-segmentation has achieved for these 6 VMs. The first two using Mac VLAN, second using Linux Bridge interface isolation, and the third is using OpenFlow rules to enact our isolation between different VMs. So I could move these around. I could do a migration if I want to. The only problem is that apart from Mac VTAP, the other two will have to have their isolation settings reconfigured or their OVS flow table entries reprogrammed as well. So microsegmentation is possible using Linux kernel interfaces, and sitting above this, other orchestration platforms, other tools, OpenShift, OpenShift V, Incus, you name it, are probably relying on these underlying techniques to actually perform isolation. So really it comes down to whether those tools can allow us to configure a Mac VTAP mode of private, or if they can actually perform Linux Bridge interface isolation for us, or allow us to program OpenFlow rules in a programmatic sense, especially with migrations as well. So I can look at tools like Incus as well. I'm going to skip over these next ones. EV tables is the same. We can create 2 VMs and we can simply make a layer 2 ACL that restricts those 2 machines from communicating with each other. I'll make these slides available so you can step through this if you want to. So my conclusions around this would be that Mac VTAP is really the only technique that's easy to exploit with no additional configuration for isolation of VMs that supports migration of workloads. Now, when we migrate a VM from one host to another, the underlying physical interfaces, those logical interfaces, or the logical interface VLAN 10 in this case, would need to be identical everywhere. So that's probably the only caveat. Apart from that, it provides the most optimal latency profile as well. and it removes the reliance on trying to keep track of existing interface isolation status as well as OVS or OpenFlow rules. So Mac VTAP is probably the simplest to configure and the best approach from an isolation perspective. Now it's up to us to understand which virtualization vendors support the ability to configure this mode of operation, as well as whether they will support this for production deployments as well, because some vendors may have their own approach on how they want to achieve microsegmentation as well, which would be in contrast to the approaches that we could take with tools like the CX10000. If I look at containerization, we start looking at things like LXC, Incus. LXC is a containerization method, and the management of this is things like LXD. I probably should put LXD here as well. Or these days, Incus as well. So LXD was taken back in-house by Canonical or Ubuntu, and the license has been changed. So the original developers of LXD have split and forked this code off to create Incus, which now has a true open source license as well. So when we start looking at LXC containers, we can leverage Mac VLAN as well. We can also use the same approaches with Linux bridges, as well as OBS. But we've quickly seen that Mac VLAN is probably, or Mac VTAP, and its underlying technology, Mac VLAN, is probably the most efficient way. LXC containers, Incus, operate inside their own namespace inside the system. They're not operating inside the kernel. So a little bit different. They actually leverage the existing kernel and existing modules of the host. There is an API which is REST-based to talk into these systems. Likewise, the LXD API can configure logical interfaces as well that are attached to the lower interface. Again, it can't configure the underlying logical interfaces, so we need to make sure they exist already. But apart from that, the underlying networking stack remains the same. So you can see that when someone says, do we support isolation for KVM or Docker or LXC or CRI or whatever, it's actually these underlying Linux networking stacks, tools and modules that really influence how we can steer traffic through the network. So let's have a look at how this is configured with Incus. So it's actually very similar if we look at how I have to have already pre-created and pre-positioned my logical interfaces. Now these already exist because I've just configured this for my KVM interfaces. I have to create a profile. So these probably already exist on my system, but we'll go through and just have a look. We create the profile, which I already have created before. We have to add that inside the profile. We now have to attach a logical interface called Ethernet 0, which will be assigned to my VMs using this profile. The network type will be a Mac VLAN. The mode will be private, and my parent logical interface will be VLAN 10. So I should be able to look at this profile. Show, okay. What is the command? I think this is profile, Incus profile, list. Right, there we go. I thought I did that. Okay, so I've got this profile called Mac VLAN here. I can do a show Mac VLAN update. So this profile is going to assign an interface to containers called Ethernet 0. It'll be a mode private, and I've typed Mac VLAN using VLAN 10. Now, one thing to look at here as well is that Incus, as of version 6.6, supports this mode type of private. If you're running a version less than 6.6, you won't have the ability to do isolation for containers or VMs. And if you're using the canonical LXD implementation, they have not implemented this type of operation of mode type private either. So Incus 6.6 is where it's at for that. So my profile is here. I'm going to launch my containers. Okay, so I'm going to start a Linux Alpine container called C1 that'll have the profile of Mac VLAN attached to it. Why is that not working? It does exist. Oh, okay, right, cool. Okay, Incus will send containers across multiple members of the cluster. So as you can see, it's working on C1, oh sorry, it's working on server 1 and server 2, which is this one. But server 2, which is also a member of my Incus cluster. Oh, I need to be root, okay. Cool, it's operational, but it doesn't have a VLAN interface. No, okay, cool, that's easy to fix. Let's do this. ES18 here, it's up. Cool, they're all running. So we can see now that we have to have consistency of our underlying interfaces across everything. So if I come back and look at my profile, this VLAN interface, parent interface, needs to exist on all members of the cluster in this case. And the same would go for for KVM as well. So it's used by these interfaces here. I now have this running across 2 members of my cluster as well, which is pretty cool. Okay. Oh, right. I need to assign addresses to each of these containers. Okay, that's done. Okay, I've also written the script that's going to ping every other address, including itself, and the gateway, and then show me the out table from container 1. Okay. Okay, so okay, that is the CX10K. I think another problem is here. This is what happens when you use a virtual machine and nest your workloads. So I'm going to do this. Okay, I just need to reconfigure my these 2 machines I'm using are attached to the same, probably attached to the same bridge for ES18 here. Let's see what happens if I attach that to there. Right, that's better. So because they're attached to a software switch inside the guest system, because I'm running this as nested VMs, they're actually switching locally. Right, so moved into different switches. Okay, cool. So now I've got isolation between all of these. So I should better log into one. Now I've got micro segmentation and isolation between KVM VMs and containers. Cool. But we can take it a step further. So Incus is an orchestration platform that will let me bring up KVM VMs as well. So I can launch virtual machines. Now Incus simply just uses KVM and QEMU. So the things I was doing before with the virshell command, we actually now have a system here that can do both containers using LXC, KVM VMs, and schedule this across members of my cluster. Right, so now I've actually sent these VMs running on server 1, server 2, server 3. And I could add members to the cluster. I could move them around. They are using the same profile. Right, so now I've got containers and VMs on here. The one thing about VMs though is they do take a bit longer to start, so it may take a bit longer to get get the agent running, so I can actually put the IP addresses on them. It seems to be okay. Okay, let's try logging into VM4. I guess we could just go directly in, shall we? Cool. Okay, let's ping these addresses here: 151.152.151.2.3. Cool, and it's all going through the CX10K. Let's have a look and see what that thing showed. Log back in. Cool, lots of MAC addresses. Awesome. What are the IP addresses of these containers? 141, 42. Cool, okay. Cool. Okay, I've got micro-segmentation occurring between KVM on a single host, LXC containers, KVM VMs using Incus. Wow, okay, cool. So now I just need to go and configure policy inside PSM on VLAN 10, and I'll have micro-segmentation occurring here as well. So right now what I've actually done is I've got containers and VMs running, and if I want to run them all simultaneously I could do that. I did write this script to see if this works. Cool, okay, so it just goes through and pings pretty much effectively a full mesh and then dumps the art table for me on container 1. Should be another one as well, I think. Okay, no it doesn't. Okay, cool, that's good. Okay, so this is how we provide isolation of virtual machines directly inside the Linux networking stack, whether it's using Mac VTAP, Mac VLAN. So Mac VTAP would be preferred for KVM VMs, Mac VLAN for LXC containers, and then things like Linux bridges with interface isolation set to on, and OVS with OpenFlow rules. So we've got all these VMs running here now as well, and each have their own benefits. For my money, it really comes down to, I think Mac VTAP, Mac VLAN gives us the best approach. It supports migration between different hosts without having to reconfigure. The Mac, we just have to simply track the MAC address across the network. So I'll leave it there. Next up, we'll be talking about things like Proxmox, getting into OpenShift as well. But I think that's enough for the session. Thank you. Bye.